Hey, welcome. Today we are going to discuss one of the important graph traversal search technique, which is depth first search. To proceed further, we must know the stack data structure and their relevant operations, that is push and pop. On the right hand side, you can see an empty stack placed, which is used for keeping track of all the visited nodes. To start with, we have node A. We will push it to the stack and we will add it to output sequence, and we will mark it as visited. Now, according to the first search technique, we will check the top of the stack symbol. We will have A here, and we will check all the adjacent unvisited nodes of A. We will have B and S here, B and S. Uh, Following the alphabetical order, we will push B onto the top of the stack. Now we will add it to the output sequence and mark it as visited. Now B is at the top of the stack, and S is the adjacent unvisited node. So we will push S to the top of the stack and add it to the sequence of and mark it as visited. Now S is at the top of the stack and C and G are the unvisited adjacent nodes. Alphabetically order we have to follow. We will push C on the top of the stack and add it to the sequence and mark it as visited. C has D, E and F as adjacent unvisited nodes. So alphabetically we will push D onto the top of the stack and add it to the sequence and mark it as visited. D being at the top of the stack with C as the only adjacent but visited nodes. So there is no other than E. We will pop it up from the stack. Now we will have C at the top of the stack and E and F as the adjacent elements of C. So we have pushed E alphabetically first and added to the sequence of output and marked as visited node. E has H as adjacent element which is unvisited. We will push it to the top of the stack and we will add it to the sequence and mark it as visited. So here we see H has G, so we will push it to the top of the stack and add it to the sequence of output and mark it as visited node. Now at the last we will F unvisited node. we will push it on the top of the stack, and we will mark it as a visited node and show on the sequence of output. Now F is the top symbol of the stack, and F has both C and G has visited node and adjacent nodes, so we will pop it off. Similar is the case with G, we will pop it off. Similar is the case with H, E and C, so we will pop consecutively C, same as the case with A, and we will have reached the last symbol of the stack, which is A, so we'll pop it off A also, and that's it. Stack is empty. This operation will signal the algorithm to stop, and this is how the depth first search algorithm works. You can see the output sequence produced below here. This is the output sequence. So thank you for watching. In this section we are going to discuss breadth first search, or BFS. As in the given example, the BFS algorithm traverses from A to B to E to F first, then to C, and G lastly to D. It implies the following rules. Rule number 1. Visit the adjacent unvisited vertex and mark it as visited, and display it, insert it in a queue. The next rule is, if no adjacent vertices is found, remove the first vertex from the queue. And rule number 3, repeat rule number 1 and rule number 2 until the queue is empty. So here we have steps, traverses and descriptions. In the first image you can see here, just initializing the queue. Sorry, here. And the second one is, we start by visiting is, means starting nodes and mark it as visited. Here this is S. So in the third step we have just this shape, and then we see an unvisited adjacent node from S. In this example we have 3 nodes, but alphabetically we choose A and mark it as visited. In fourth step we have just this shape, and next then unvisited adjacent node from S is B. Here this is B, unvisited adjacent node from S, we mark it as visited and enqueue it here. Here we just enqueue. In the fifth step, in this section we have unvisited adjacent node from S is C. Here this is C, We just mark it as visited and enqueue it here. We just enqueue here, and in the sixth step we have this shape. Now S is left with no unvisited adjacent nodes, so we dequeue and find A. So in the seventh step we have this shape. From A we have D as unvisited adjacent node here, and we just mark it as visited here and enqueue it here. So at this stage we are left with no unmarked or unvisited nodes, but as per the algorithm we keep on dequeuing in order to get all the unvisited nodes. When the queue gets emptied, the program is over. So thank you for watching. Allah Hafiz. So our next topic is cross-call algorithm, a minimum spanning tree using cross-call algorithm. So in the given graph we have to find the minimum spanning tree. So first of all we have to keep in mind these 3 points, which is the first one, all the minimum spanning tree is a subgraph such that all vertices of the graph exist in a subgraph. This is the first point that we have to keep in mind. And the second point is subgraph should be connected. And the third one is there should be no cycles in subgraph. Means there should be a missing edge between vertices. So basically we have to keep one thing in mind, which is including minimum edges, no cycles. In the given tree, first of all we have to draw all the vertices. Here we have A, B, C, D, E, F and G. So first of all we see the minimum edge between F and G vertices, which is 1. Sorry, between the B and D vertices, which is 1. And the second one is we have to choose the edge between F and G here. We have to connect it and we have to write the value, and also the third one is between A and B vertices, which is 2. We have to connect it, and also we have another 2 here. We have to connect it here, and we have to show the value, which is 2. And then we have 3 here. So basically If you connect E and B vertices, there should be a cycle, and we are not going to consider it, and we have to draw. Just we leave it, and the other edge which is between A and D, if we connect A and D, so there should be a cycle. So we have to prevent this point, and we have to just do not consider it, and between, and the other one is, we are going to see between A and F vertices, which is 5, and if we connect A and F, there should be a cycle which we have to prevent it. So we just cross it and go to another one. So the other one is between G and C vertices, which is 6, and we just connect these two vertices, and we just write the value, which is 6. So finally we draw the subgraph here. This is the subgraph. So finally question arises here, why we do call it minimum spanning tree. So the answer is just simple. The edges that we have included here, uh, those edges should be minimum. So at the end we just finding the weight of the edges, which I conclude here: 1 plus 1 plus 2 plus 2 plus 4 plus 6, which is equal to 16. So weight is equal to 16. Thank you for watching. In this section we are going to find out the shortest path in the graph by using Bellman-Ford's algorithm. This algorithm solves the single source shortest path problem of the directed graph. That graph which has vertices and edges, in which the edge weights may be negative. Moreover, this algorithm can be applied to find the shortest path if there does not exist any negative weighted cycle. So the following example shows how the Bellman-Ford algorithm works step by step. This graph has a negative edge but does not have any negative cycle. And also the problem can be solved using this technique. At the time of initialization, all the vertices except the source are marked by infinite and the source is marked by 0. So this is our graph. In the first step, all the vertices which are reachable from the source are updated by the minimum cost. Hence, vertices A and H are updated. In the next step, vertices A and B, F and E are updated. Following the same logic, in this step, vertices B, F, C, and G are updated. Here vertices C and D are updated. Hence, the minimum distance between vertices between vertex S and vertex D is 20. Based on the predecessor information, the path is S from S to H, from H to E, and from E to G, and from G to C, and from C to D. So this was exactly the Bellman-Ford algorithm.